started. So as last Wednesday, we have the pleasure to have two guest lecturers. The first one is Matthias Beck, who didn't have to come from so far away. He's at San Francisco State University, and he'll tell us about combinatorial polynomials.
Thank you. Thank you, Raman, for inviting me here, and Aaron. So let's see. So my plan is to give sort of half a survey talk about classification of polynomials in combinatorics, and half sort of new results with Katharina, whom you all know, and our joint student, former student, Emily McCullough. And so the motivation is very simple. You have a class of polynomials that somehow occur in nature. Let's say you really like graph colorings, and so you really like chromatic polynomials, and so the question is, which polynomials are chromatic polynomials? So, yeah, so somebody hands you a polynomial and asks you, can you cook me up a graph that has that polynomial as the chromatic polynomial? Yeah, so this is what I mean by classification problem. And so one goal is I'm going to try to convince you that you've done some of this already in the last week and a half. That's one goal. But what I want to show you is sort of is a lot more sort of down to earth. And so I want to concentrate on Erhart polynomials, which you've also seen. But let me just set the stage. Yeah, so this is a theorem that I think Raman proved yesterday or the day before in much greater generality. So I like to be very concrete. So what I'm going to do is I'm going to fix a lattice polytope. So that means that I'm in some d-dimensional space, and the vertices of my polytope are on the integer lattice. Okay? And so the polynomial I'm interested in is the counting function of the lattice points in the polytope as you dilate. Okay, so maybe I should start making corrections to my slides over here. So I think of t as a positive integer coordinate. Okay, and so now I take my polytope and just start making it bigger and bigger. So t times p is just dilation. And so I want to count now lattice points in these dilated polytopes as in the parameter t. Okay, and I think of this t as an integer because I don't want to destroy structure. So I have my vertices are lattice points, and so if I'm dilating by an integer, I get lattice points again. Okay, and so this is Ehrhart's famous theorem that Raman proved, again in bigger generality, is that this is a polynomial. Okay, so this is a polynomial, and then once you realize it's a polynomial, then the degree has to be the dimension. That's how this function grows. And the leading coefficient has to be the volume, because that's sort of approximately how your lattice point count grows. And he also proved that the constant term is 1. And for you, I can tell you that this 1 is the Euler characteristic of the polytope. So this 1 is not just a simple number 1. This actually this is a meaningful 1. Okay? And so I don't know. I mean, you've done this now for too long, but if you pretend you've never seen something like this, you should be totally amazed. There's no reason why such a function should be a polynomial. I mean, in fact, if you pretend that you've never seen a chromatic polynomial, and you just took a course of graph theory, and somebody tells you, you count these proper colorings in terms of some parameter, and it's a polynomial, you should be just as amazed. There's no reason why this should be a polynomial. Yeah? But that's not very deep. So the chromatic polynomial, you probably proved that as an exercise in your graph theory class. This is slightly deeper, so this is a non-trivial theorem, but not super deep. And again, you know at least one proof. But so I want to point that out. So this is already some sort of magic. But now I want to use this magic and say, okay, can you somehow classify which polynomials appear here? Yeah. So here's, if you want, is a research project that I don't encourage you to do, because this is not going to be solved in your lifetime. Yeah. So I'd like to say, okay, here's my favorite family of polynomials, and so I'm going to ask now the same question that I asked about chromatic polynomials. Is like, if you now hand me a polynomial, and you ask me, can you cook me up a lattice polytope that has that polynomial as your Erhart polynomial? So that's the kind of classification problem I want to ask. Yeah? So the first thing I'm going to do is I'm going to look at the constant term. If it's not 1, I say no. We'll have a cup of coffee. The second thing I'm going to say is, okay, is the leading coefficient something positive? If it's not, I'm going to have a beer. Stuff like that. But so I want to, I want to have more machinery. Yeah. Okay, I should have started by saying you should just yell at me if you have any questions or complaints. So the more I get to write on this board, the better. Okay, so now if you think about this question, it's a good thing to have machinery in terms of like, what does it mean to know a polynomial? So here are 3 ways I like to think about polynomials, and at least 2 of them. So one way to know a polynomial is if you tell me the coefficients. Another way, if you tell me the roots. Well, for the roots, you have to give me one more piece of information. But in this case, we have a constant term. We know what the constant term is, so that's enough. Yeah. So if you give me the roots of a polynomial, then I know the polynomial. Okay. And so for this hour, it turns out the best way of writing down a polynomial is this funny basis. Okay. So here's a basis. I'm fixing d as my degree, or my maximum degree. Okay. And so t is my variable. Then I claim these d plus 1 binomial coefficients over here, they form a basis of the space of polynomials of degree at most d. And so I'd like to call these coefficients h0 star through hd star, because everybody calls them this. Well, 90% as well calls them this. And there's another way of thinking about, so this is just a change of basis. You can think about that way. But there's sort of an arithmetic way to think about this. So if you have a polynomial and you embed it into a generating function like this, then you can convince yourself this will always give you a rational function. And it's a rational function with this denominator. So if you have a degree d polynomial and you write it just as a formal power series, then it turns out you can write this as a rational function with this, sort of the denominator is sort of clear a priori. So then the question is, what's this numerator? And I claim this numerator is a polynomial with exactly these coefficients down here. Okay, so this is so the linear change of variable from here to here is the same change of variables as going from the polynomial to your generating function. Yeah, this turns out to be the same thing. Okay. So this has some advantages. Okay, and I'll tell you in a moment why I like to write my polynomials this way. But let me convince you that this is a hard problem. So I'm going to show you what we know in dimension 2. Okay, so in dimension 2, so let me go back here. So in dimension 2, I have 3 coefficients. but the constant term is 1, so I don't need to talk about that. So what you see here is a graph of I'm graphing two coefficients. So here's the quadratic coefficient, here's the linear coefficient, and what you see here is a picture of all possible degree 2 Erhart polynomials. Okay, so in the following sense, so you can convince yourself that a degree 2 Erhart polynomial, so these coefficients over here, they have to be half integers. So that's, just take my word for it. And so in this graph, you see a bunch of lines, a bunch of rays, and sort of a region, and then there's this funny point. And so what I really mean by this graph is every half integral point on this graph gives you two coefficients that belong to an Erhart polynomial of a polygon. Okay, does that make sense? Yeah. So give me any point in here that either has integer coordinates or half integer coordinates, and this will belong to actually a lattice polygon that has these two coefficients as the leading term and the constant term. Okay. So let me, for those of you who know a little bit about Erhart polynomials, let me give you some idea what's going on over here. So down here, this is the point 1/2, 3/2. Yeah, so this is so the area is 1/2 and the leading coefficient is 3/2. So this is the Erhart polynomial that belongs to sort of a standard triangle. Okay, so a triangle with these vertices. Okay. And so now, if you go off this way down here, what are we doing? We're increasing the area, but it turns out, so I'll show you this in a moment too. So this linear coefficient has something to do with the number of boundary lattice points. Okay, and so what we're doing over here is we're keeping the number of boundary lattice points. There's 3 of them. Okay, and we're increasing the area. So the polygons that belong to points down here are triangles that have arbitrarily large area, but no lattice points on boundaries other than the 3 vertices. Right? You can cook this up by sort of like having some GCD conditions and stuff like that. Okay, so that's down here. And what's going on over here? So over here, we're increasing area just as much as we have to if we want to increase sort of the number of boundary points, sort of just most possible things. So these are polygons that look like this. So if you want to have a maximum number of boundary points by keeping the area minimal, I claim you have to do something like this. And if you don't like an even number of boundary points, you can do this. Yeah. And so these are the polygons that you see up here. So again, these two coefficients, they each belong to a polygon that looks like this. Okay. And then you might ask, what's this point over here? So this point is the point. This point is the point. Well, I can tell you the polygon it belongs to. So this is the polygon that belongs to this triangle over here. So I guess it's the point. I shouldn't try to compute live. So so this turns out to be the unique triangle that has exactly one interior lattice point. Yeah. Well, exactly one interior lattice point and still a maximum number of boundary points, I think. Anyway. Yeah, so if you compute the Erhart polynomial of this triangle over here, you're going to get these coefficients, whatever they are. and then there's this funny ray over here. So this is an empty space over here. So over here, the only point that we can realize as a coefficient vector is this point over here. And then over here in this area, we can realize everybody. Okay. And so this follows from two theorems. One is Pick's theorem that some of you know. That has to do with this sort of two-dimensional lattice point game. And there's an inequality due to Scott, which is now 40 years old. And this inequality gives you exactly this ray over here. And the inequality has something to do with once you have some interior lattice points, except for this case over here, there's sort of there's an additional constraint over here. Yeah? My point of this picture is not really to. I shouldn't try to explain it too much. My point of this picture is, this is a weird picture. So this, yeah. So it's not exactly trivial, this classification problem. Yeah? But okay, this is solved in dimension 2, and we don't have this picture in dimension 3. Okay, so here's an open problem. I'd like to see the same picture in dimension 3. Okay, so we don't know this. We know some constraints. But whatever constraints we know, there are some points that we sort of have to take out. There are some exceptions. And we don't have a full classification. Yeah? So maybe that's something that will be solved in your lifetime. Yeah, so classification problem in dimension 3. That would be kind of cool. Aaron?
Yes. But do you know that there are only finitely many exceptions?
No, we don't know that. Yeah, we don't know that. I think we don't know that. Yeah, it's a good question. Yeah. Yeah. So this is an active area of research, and well, I'll tell you a little bit about this as we go along. Any questions? Okay, so here's another piece of machinery. I'm not sure have you talked about this? Okay, so it turns out there's sort of a symmetry relation in this world. So this is a theorem that was conjectured by Erhart, and he proved this in many cases. But the general proof is due to MacDonald. So once you know that something's a polynomial, you can plug in negative numbers. Okay, just algebraically. Okay, and so it turns out that this is a beautiful theorem. If you do this for the Erhart polynomial up to a sign, you're counting interior lattice points. Okay, so it's kind of like once you have this polynomial, you get sort of 2 for 1. As your t goes up, you're counting lattice points everywhere, and as your t goes down into the negatives, you're counting lattice points in the interior of your polytope as you dilate it. Okay, and so again, you can translate this in terms of my favorite basis, except that you have to shift the basis a little bit now. Okay, so it turns out if you translate this in terms of my change of variables for the H star coefficients, basically what you're doing is you're turning the coefficient vector upside down. Yeah, and in fact, so you've seen this last week. Yeah, so there's a reason why this we're using the letter H, so there's some sort of analogy with the H vector of a polytope or a simplicial complex, and there's some sort of similarities, but not exactly everything the same. Okay, so but you should think of this as some sort of a version of duality. Okay. Okay, and so now we're coming to the theme of what you're doing over here. So here's the first sort of general classification theorem. This is due to Stanley. He proved that those H star polynomials are always non-negative. Okay, so So, yeah, so number one, this is a beautiful theorem. It's a sort of a beautiful structure here. Yeah, but again, I want to think about this in terms of classification. Yes, so this theorem now tells me that, you know, if you hand me a polynomial and ask me, is there a lattice polytope that has this polynomial as your Erhart polynomial? What I'm going to do is I'm going to express your polynomial in this basis, and so just see if I have a negative coefficient somewhere. If I do, next beer. Yeah. And this theorem also has some other consequences. So I claim when you have a theorem like this, and maybe you've seen examples like this last week already, but if you have a theorem like this, you can prove some existence theorems. Okay, so for example, so I claim if you have something that you want to model with a polytope, with a lattice polytope, and you're just interested in the existence, say, of an interior lattice point. Okay, so maybe your original polytope does not have an interior lattice point, but you know, somewhere there's a parameter, and this geometrically this parameter is a dilation parameter, and you're asking me, okay, at some point, you know, I'm guaranteeing you there's an interior point, and you're asking me, okay, is there an interior point at dilate number 3 or something like this? Okay, and so I claim this theorem by Stanley, this kind of positivity theorem, helps you with this type of question. So I claim the kth dilate of P contains an interior lattice point. I think it's an if and only if. This coefficient in the H star basis is positive. Okay, so the reason for this is your binomial coefficients over here are very nice. So the binomial coefficients, if you think about this for a moment, if you plug in sort of positive integers t, then your binomial coefficients are either 0 or positive. So particularly they're never negative, and so by knowing that these coefficients are non-negative, you're just adding things here. You can stay in first grade. You don't have to go to second grade when you start subtracting. It's annoying, right? And so if you're just adding, then having sort of an actual positive coefficient, okay, means you can make existence claims like this. Okay? And this is a little bit sort of goes along. So again, this philosophy is not restricted to Erhart polynomials. This philosophy goes a little bit along, you know, I mean, some of you know the story, but you know, why is there a chromatic polynomial? So the chromatic polynomial was constructed by Birkhoff because he wanted to prove the four-color theorem. Yeah, so the chromatic polynomial was sort of a byproduct of somebody trying to prove the four-color theorem. And then people said, "Whoa, this is kind of cool. There's a polynomial over here." Yeah, and so what Birkhoff was trying to do is he constructed a polynomial where he wanted to make some statements like this, exactly like this. He wanted to have an existence statement. You know, if you take a planar graph and you plug in 4 into a chromatic polynomial, you get something non-negative. You get something positive. Okay, so this is sort of just a remark. And so let me give you a refinement of this positivity theorem. In part because I want you to apply this to other situations. Okay, so here's a theorem that has the Stanley theorem as a corollary. Okay, so this theorem first surfaced in a paper by Beck and McMullen. So these are names that you know by now. But this was one of those papers that sort of was not understood at the time, was ahead of its time. And so this was really understood in some sense by Alan Stapleton a couple years ago. So I'm giving you one version of the theorem that has the condition that the leading coefficient of the H star vector is not 0, but there's a sort of a more general version that's actually due to Stapleton alone. So for which you don't need this condition, okay? But let me just give you the simple version. So the simple version says the following. So I do the following thing. Take a polynomial. So I want to think of now my h star vector as sort of the numerator, because I want to actually think of it as a polynomial, and not necessarily in a standard basis, not as a polynomial in this binomial coefficient basis. Okay. So take a polynomial and play the following game. You can do this for any polynomial. You write it as a sum of two palindromic polynomials. Palindromic means they're symmetric coefficients. Okay? So you can give this to your calculus students or linear algebra. Do it with your linear algebra students. If you're TA linear algebra, next time you should give them this exercise. Did you know this fact? You can always do that. Give me any polynomial. You can write it like this as a sum of two polynomials, and those two polynomials are. It's a pretty cool fact, no? So that's not the theorem. The theorem, so palindromic, so here's one way to write down palindromic. So I'm cheating a little bit because, right, so, do I want to spend time on this? Yeah, let me spend a little bit of time on this. So h star is a full degree polynomial because I'm saying the dth coefficient is actually non-zero, okay? And so the way I'm writing this down, I claim, and also my constant term over here is 1. So I claim this a polynomial has to be a full degree polynomial. So your a polynomial is just a full degree, nice palindromic, has symmetric coefficients. Yeah. But the b polynomial for all that matters could be a 0 polynomial. For example, it could be that h star is already palindromic. Then in my decomposition over here, I can just choose a to be h star and then b to be 0. Okay. But b, the 0 polynomial is a palindromic polynomial. Yeah. And so when I write this down, I'm not saying anything about the degree of b. I'm just saying it has this sort of symmetry. It has a symmetry about d minus 1 over 2. Okay, so you can do this for any polynomial. The theorem is this word non-negative over here. Okay, so the theorem says that if you do this decomposition, your a polynomial and b polynomial have non-negative coefficients. Okay, so that's stronger than saying h star has non-negative coefficients. Correct? So h star having non-negative coefficients doesn't mean that over here you have non-negative coefficients. Could be some sort of funny combination. Yeah. And so this is a stronger theorem. Yeah. And so if you have questions after I leave today about this theorem, you should ask Andres. He's one of the world experts on this theorem. Yeah. Okay. So this is sort of a refined positivity theorem. Okay. And so here's maybe the biggest open problem for you, or the biggest charge for you. I would like you to try this decomposition on any polynomial that you come across that has non-negative coefficient. Okay, I think people don't do this enough because they don't know this, linear algebra exercise. Yeah. So here's what you should do. You should, like, why are we interested in having positivity questions when we talk about polynomials? Okay, I'm just talking about polynomials now. Okay, so here's, here's your favorite, family of polynomials, and Aaron, a couple years ago proved that they have non-negative coefficients. Okay, so why are we interested in this? Well, because that tells you something about which polynomials sort of show up in your family. Okay, in this case, I would like you to try this, and then try to prove this refined version of that. Yeah. Yeah. So this is my charge to you. Okay. So what Beck and McMullen showed is in the Erhart case, this works. You can do that, and you get a stronger theorem than just positivity. Okay. And so, okay, maybe one more word is like, why do we care about this? Well, again, sort of, this gives you more information about your family of polynomials. And if you don't like this sort of palindromes, you can write down what this means in terms of your coefficients of your polynomials. So if you unravel this, what this means about your polynomials, the coefficients satisfy some sort of inequality, linear inequalities. You can sort of, if you're really a weird mathematician and you don't like palindromic polynomials, you can sort of unravel this and then state this theorem purely in terms of your family that you're interested in. Okay. So what's the next step? So now I want to stop here and say, okay, this is how far I want to go with positivity. What's sort of the natural next step you could ask in terms of classifying polynomials. And so one natural thing that you've probably talked about also this week and last, is unimodality. Okay, so for me, unimodality is always about polynomials, so I'm going to call a polynomial unimodal if the coefficients go up and then go down again. Yeah. And so what I have in mind now is a classification theorem of the sort, like, if your polynomial is in this family, then the coefficients are unimodal. Yeah? So that means that in that, again, unimodality sort of helps me to classify polynomials. So, if there's a polynomial that supposedly is in your family, and I look at the coefficients and it's not unimodal, then I'm going to tell you I have bad news for you. It's actually not in your family. Yeah? And so the crucial example over here in this game, at least for people like Katharina and me, is real rootedness. So it turns out if your polynomial only has real roots, that's stronger than having a unimodal coefficient sequence. Yeah, so it's a nice little exercise. I guess now you can really give this to your calculus students. Okay. And so let me tell you what's sort of known in the Erhart world. So if I now look at this H star polynomial, so again the H star polynomial is I want to think of this here as an actual polynomial. Okay? So H star in general is not unimodal and not real rooted, but sort of people have sort of started to come up with conjectures that this H star polynomial is unimodal for certain subclasses of lattice polytopes. Okay, and so I wrote down 5 subclasses, and this is supposed to be a poset. So, excuse me. So my classes go wider as I go down, and I guess they go wider also from order polytopes to Arkhov polytopes. So let me tell you what these are. So a hypersimplex is just the unit cube in d-dimension, where you cut it with a hyperplane the sum of the coordinates equal to k. Yeah, so a hypersimplex comes with 2 parameters, k and d. D is dimension, and then k is this animal over here. And so if k is equal to 1, you just get a d minus 1 dimensional simplex. And so that's why they're called hypersimplices. What's an Alkov polytope? An Alkov polytope is one where each facets, hyperplanes, are of the form either excuse me. I need a constant in here. So either of the form xj minus xk equals some constant, or xj equals some constant. And I guess I want those constants to be integers to make it a lattice polytope. Yeah? So you can realize that a hypersimplex, you can almost see this here. You can realize a hypersimplex fits this description. Well, that's not quite true. That you can see it here. That's not true. Okay.
For the relation between the modality and real-rootedness, so you assume no negativity of the positivity of the H number?
That's a theorem, right? So that's a good question. I would only ask unimodality question when your coefficients are already non-negative, but some people might not require that.
But generally, it's not true that real-rootedness implies.
Oh, excuse me. Yes, that's true. That's right. Up here, thank you. So for my crucial example, I have to assume that my coefficients are non-negative. Thank you. So mine are, so I don't even think about that. Okay. What's an order polytope? So an order polytope is a polytope that comes from a partially ordered set. What you do is you're taking a favorite partially ordered set, finite partially ordered set, and you again go into the unit cube and add inequalities that sort of correspond to your poset. Yeah. So if you have a relation in your poset between j and k, and j is below k, then you just add inequality xj less than or equal to xk. Okay, so you sort of a geometric version of a poset. Yeah, and so now I guess you can immediately see that an order polytope is of this form. Okay? You have these kind of facets. And so, okay, more general families are polytopes with unimodular triangulations. So a unimodular simplex is one where if you're in d dimensions and you're standing at one vertex and you look at the other d vertices, then these vectors form a lattice basis. So they don't just form a basis of r to the d, but of z to the d. That's a unimodular simplex. Okay, so these are very special. And so unimodular triangulation is a triangulation into unimodular simplices. Okay, so in general, if you just pick up a lattice polytope on the street, it will not have a unimodular triangulation. But those that do, there's a conjecture that H star for those is unimodal. Yeah. And there's one more general family of polytopes. They're integrally closed polytopes. Some people call this the integer decomposition property. So what's that? So that's the property. It looks a little funny, but it actually has geometric meaning. So it's a property that any what's going on? Yeah. So any if you give me any integer point in k times your polytope, this can be written as a sum of k points in the integer points in the original polytope. Yeah, for some. Yeah, so somehow the lattice point structure in your dilates is somehow governed by the lattice point structure in the original polytope. That's what we're saying over here. Okay. Anyway, so take my word that. What's that? So for example, you can realize that the unit cube satisfies this. Yeah? So if you take the unit cube, take k times the unit cube, give me any integer point in there, I can write it as, it's non-trivial, I can write it as a sum of k. Actually, it is trivial, I think. Yeah, so if you take k times the unit cube, right, if you give me a point in here, so what does that mean? That we have every coordinate is somewhere between 0 and k, right? And so now what we're saying is we can cook this up as a sum of lattice points in the original polytope. So you can do this greedily, right? By saying, okay, I can use the all ones vector, and then I introduce some zeros. Yeah. Let me give you another picture, since you're brave enough to ask a question. So I'm guessing that at least in Roman's lecture, you've seen a construction where you cone over a polytope. Okay, so what you do is you take a polytope, and so in my picture, my polytope is two-dimensional, and I want to associate a cone with that one dimension higher. So what I do is I'm going to take my polytope and lift it at height 1, and now form the cone over it. Yeah. Yeah. So why is this nice in my world? Because now didn't plan on using 3 colors, but here they are. Yeah. But now, oh boy, whatever. So if I go at height k, what I see up here, if I cut at height k, I see k times the polytope. Yeah. And so this intercally closed business, if you unravel this in this world, what this means is now, if you give me an integer point up here at height k, yeah, then it's the sum of k points down here at height 1. Yeah. So if you're algebraically minded and you deal with semigroups, I'm making a statement about semigroups over here. Because a cone, the points in a cone are a semigroup, because if I add 2 things, I stay in the cone. Yeah. But now what I'm saying is that my semigroup over here, my semigroup is actually generated. Excuse me. There's a semigroup of integer points in my cone, and that's actually generated by integer points at height 1 down here. Yeah. So that's the kind of statement that I'm making over here. So there's 2 pictures. Anyway, so there are sort of increasingly hard conjectures. They're all open. So already for hypersimplices and order polytopes, we don't know any examples of Ehrhart polynomials for which H star polynomial is not unimodal, but we can't prove it in general. Yeah? And like Aaron said, so if you can prove that they're real-rooted, that would be good enough, because we know that H star coefficients are non-negative. Yeah? And so because these classes are getting wider and wider, these conjectures are getting more and more general. Okay. So so here's some open problems if you care about this sort of question. Let me tell you at least one theorem that Katharina and Emily and I proved, and this starts with the following theorem. So this was, I guess, motivated by this last conjecture for this last class. So I showed to you that the unit cube is intercally closed, and you can realize that any parallel pipette is intercally closed. Yeah, so I need to assume that my parallel pipette still has integer vertices. Okay. And so the theorem that started all of this was a recent paper by Schippers and Langenhoven, and they proved that H star is unimodal for parallel pipettes. Okay, so I got that paper to referee, and that's what started this process. So I got this paper to referee, and I first thought that this can't be new, because I said, okay, parallel pipettes, that's not really complicated. It's really just cubes, a little more complicated than cubes. And so I knocked on my office neighbor's door, Joseph Kubeladze, who was an expert on this integrally closed question, and I said, can this be new? And he said, yeah, this is non-trivial. But anyway, so the paper eventually got published, but I thought it was kind of complicated. And then, when you're old enough, when you get a complicated proof like this, you give it to your students and say, hey, could you see if we can make this any simpler? And in my case, I mean, I had a very, very smart student who was sitting over there, and sure enough, she simplified the proof in about, I don't know, 2 weeks or something like that. So that's how the story got started. There is a crucial ingredient in this world, and that's Eulerian polynomial. So I'll have the definition of an Eulerian polynomial in a moment, but for now, let me just say that an Eulerian polynomial for me is the h star polynomial for the unit cube. Okay, so that's one definition of an Eulerian polynomial, and it turns out, if you understand Eulerian polynomials enough, then you can understand sort of h star polynomials for parallelepipeds. Okay. So what's one of our theorem anyway? Is we prove real-rootedness for the h star polynomial for zonotopes. So a zonotope is sort of a generalization of a parallelepiped. It's the following thing: you take a bunch of vectors, and you take the Minkowski sum. Okay, so that's what I'm doing over here. And if my vectors are linear independent, I get a parallelepiped. Yeah, but if they're not linear independent, I get something that's more general. So that's one thing that we could prove that came out of the simplification for the parallelepiped proof. And another theorem that I want to show you is again sort of a little bit towards a classification question. So we ask ourselves the following question: can you classify h star polynomial of zonotopes? Okay, and the answer is no. There's another open problem, but at least we can sort of classify one direction. Okay, so we can give you the convex hull of all the h star polynomials. So the way I think about this is you're fixing a dimension, and I'm fixing a class of polytopes, zonotopes in this case. Okay, I know my h star polynomials, they all have a constant coefficient of 1, so let me forget about that. And so I take the rest of the coefficients and think of them just as a vector in d-dimensional space. And then I can ask, okay, if you take all these vectors, what's this look like? And so the convex hull of these vectors has a very simple description. It's a simplicial cone with this apex over here and d generators. And these generators are the coefficient vectors of refined Eulerian polynomials. Okay, so now I can tell you what an Eulerian polynomial is if you don't care about unit cubes or Erhart polynomials. So an Eulerian polynomial, let me do this over here maybe. So maybe I'll use the notation A of d comma z. So without the j just yet, so an Eulerian polynomial is the following. I'm looking at permutations on d elements. So SD is just a symmetric group, and I'm asking, okay, which of these have d descents? Okay, k descents. Excuse me. And so, I have to tell you what is a descent of a permutation. Many of you know this. So what I'm doing is I'm writing down my permutation in one-line notation, and I'm just looking at where the numbers go down. So, for example, for d equals 3, I have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Yeah, so a descent is where the numbers go down. So the second the second index over here is a descent, because this is where my numbers go to. I have a descent over here. I have no descent in the identity permutation. I have a descent over here. I have a descent over here, and I guess I have two descents over here. And so now what I'm going to do is I'm going to count all permutations with k descents and stick them into a generating function. So in this case, what I would get is the beautiful polynomial 1 plus 4z plus c squared. Yeah? And if you're interested in connection with elementary school mathematics, you should ask me over lunch where these numbers show up. Okay, so what's the refinement that we have over here? So the refinement is now, I'm telling you what the last entry is of your permutation. Okay, so my last entry is some number between 1 and d, and for some reason I want to have sort of a negative j in there, and so my j just says my last entry is this number d plus 1 minus j. Okay, and so if you now just take these polynomials over here and just add them up without thinking about cones or something like this, the sum of them will give you exactly this Eulerian polynomial. Yeah, so this is I'm taking this polynomial and I'm writing it as a sum of polynomials according to what the last entry is of your permutation. So if you do that, and if you think of each of these polynomials as the coefficient vectors, those are the extreme rays of our simplicial cone over here. Yeah?
So that's what on the extreme rays?
Say it again?
Can you say on the extreme rays of which polytope?
Yes. So I will tell you in 5 minutes. Yeah.
How can the convex hull of these things be a cone? Be a conical hull?
No, I wanted the convex hull. So zonotopes have H star. If you look at all possible zonotopes in a given dimension, the H star vectors get bigger and bigger and bigger and bigger. So if you just look at the H star vectors, right, as coefficient vectors, and if you look from far away, you're going to see a cone, okay? But so an H star vector always has integer entries, okay? So you see a bunch of integer vectors, and they look like, they form a cone. There's some point missing, and that's why we need to take the convex hull. Yeah, so there's something that from far away looks like a cone, but they say, there's some points missing there, and so take the convex hull, and I claim you will get this. Yeah. I don't want to take the conical hull. It's very close. I don't want to take the conical hull because my apex is not the origin. So it's a good question. Other questions? So why is this interesting? So I guess there are my Ehrhart polynomials. So it's an old fact that Eulerian polynomials are real rooted. Okay, and so I guess here's my earlier definition. So if you think of the d-dimensional unit cube, I said the Eulerian, one definition of the Eulerian polynomials is the H star vector of the unit cube. So if you take the d-dimensional unit cube and think about the Erhart polynomial, this is what you're going to get. And so here's your connection. Okay, and so somehow by saying, hey, we can understand H star polynomials of zonotopes through Eulerian polynomials, then we can use the fact that Eulerian polynomials are real rooted, and that gives the first theorem that I showed you. Let me show you maybe 3 more things. So let me show you my favorite way of viewing this identity over here. So why do these Eulerian polynomials show up in this sort of geometric world? And the reason is that there's a very natural triangulation of the unit cube. So if you take the unit cube and sort of want to triangulate, so here's one way to do that. Is you just stare at any point in a unit cube and you see how the coordinates are ordered. Yeah, so the coordinates follow some order, so that's a permutation. So my coordinates are somehow ordered by some permutation. Okay, and so if you ignore the second line for a moment, by going over all permutations, and I'm saying everybody is between 0 and 1, I will get a decomposition of my unit cube. Right? So every point in a unit cube, falls into one of these things, and those are simplices, if you think about this for a moment. And then it's a wonderful fact of life that you can make this decomposition, a disjoint decomposition, by forcing a strict inequality if you have a descent. Okay, so this is something Katharina could give you as a homework, let's say. Okay, so I claim the descent set is natural over here. The descent set of a permutation is natural over here, exactly for a tiebreaker. So if you leave out this line down here, you have a triangulation of the unit cube. It's the standard triangulation of the unit cube. But I want to sort of do arithmetic things. So I don't want to just have a triangulation. I want to have a sort of a disjoint union of things. And it turns out the descent set gives you exactly the tiebreakers to make this union a disjoint union. Okay. So I guess that's one ingredient that we need later on also. Let me, there's Aaron. Let me also say that these refined Eulerian polynomials were not something that we sort of came up with. As far as we know, they first showed up in a paper by Brenti and Welke, unless Aaron knows an earlier appearance of them. Do you? Okay, I think that's what we found. And so here's a case where you have a class of polynomials that are not symmetric but still unimodal. So this is a paper from a couple years ago with Martina Kupitsky. And a recent paper proved that they're real-rooted. This is by Carla Savage and Mirko Visontai. So where do these show up in our work? Well, so these refined Eulerian polynomials, they show up when you look at half-open cubes. Okay, so why do we care about half-open cubes or half-open parallel pipettes? So here's sort of a standard way of decomposing a zonotope. So I claim, so this is a theorem. So every zonotope looks like this. So this is not a three-dimensional picture. This is a two-dimensional animal. Okay, so every zonotope has sort of a natural decomposition in terms of parallel pipettes. And so now what we want to do is we want to have sort of a half-open decomposition where this union over here becomes disjoint. Okay, and so it turns out arithmetically what you want is exactly these refined Eulerian polynomials. Okay, so that's your question from 5 minutes ago. So these extreme rays, they belong technically not to zonotopes, but they belong to sort of half-open zonotopes, namely half-open cubes like this.
So when you say that you take the convex hull of all the H star polynomials, you meant it's for this larger class where you include the half-open? On the extreme rays, you don't.
At least on the extreme rays, I need that. Yes, that's right. That's right.
On the extreme rays, you don't have actual.
That's correct. That's correct. Yeah. I think we just take H star polynomials off the closed zonotopes, but then the extreme rays belong to half-open zonotopes. That's correct. Yes. Yeah. Okay. And so, I mean, okay, and so what's the last ingredient? Well, I sort of said this already. So if you have a parallel pipette, then the H star polynomial is just a combination of those refined Eulerian polynomials. So if you take this now, mix a little bit, you're going to get our theorem.
Just to make sure, so if you take only actual zonotopes, then the cone that they span is the cone that the smallest cone that contains all of them is the cone that you described.
That's right. That's right. That's right. Right? Yeah. Okay. Let me show you one more thing. Oh, yeah. So maybe I don't have to spend much time on this. So I said already, this cone is not filled out, and well, here's an open problem. Can you do better than this? But I want to show you something else, because you've been talking about valuations. So there's an extension of our theorem that has essentially the same proof, and that's for valuation. And so I guess this is what Raman proved yesterday or the day before. So an Erhart polynomial is just an example of a valuation, because if we count lattice points, that's just what it is. And so I guess McMullen proved this generalization of Erhart's theorem, that if you play this sort of dilation game for valuations, same thing works. And Raman and Katharina have this beautiful theorem that was published last year, is where they characterize valuations that are invariant under z to the d. So this is just lattice translations. They characterized valuations for which this sort of H star vector is non-negative. And so based on this theorem, so what we can actually do is we can prove that this sort of generalized H star polynomial is real rooted, as long as you give me a valuation that satisfies Raman and Katharina's theorem. So the Erhart case is just one case that falls into this category, but the same proof that I sort of outlined works for this general case. And with that, I'm actually over time, so let me thank you for your attention.
Thanks a lot. Any questions? Any questions coming up? So here also lunch.
Don't be shy.
Questions? Thanks again.
All right.